Asia is the native home of wheat, barley, oats, and all other true cereals except Indian corn. As man learned to cultivate wheat for bread, his foot became firmly placed on the threshold of civilization, using bread as the staff of life. As the cultivation of wheat expanded, civilization followed. Wheat has been ground into flour for over 5,000 years. In the beginning, a saddle stone arrangement was used in which the wheat was ground between an upper stone, held in the hands, and a lower, concave saddle stone. The quality and characteristics of bread made from this flour are shown here. Man's oldest continuously practiced industry is milling. It is a completely automatic manufacturing process to convert the wheat to flour.
This movie, The Amazing Art of Flour Milling, has been prepared by Bill Carter of the RJS Carter Company, Minneapolis, Minnesota, with the cooperation of the Department of Grain Science and Industry at Kansas State University, Manhattan, Kansas. Most of the equipment has been modified by Professor E.P. Farrell and many students and staff, and with his help, Professor Phillips, Dave Hammond, and many friends in the industry, this film has been made possible. Bill Carter has taken all the movies, edited, and prepared the film. The object of milling is to make the most favorable distribution of products from good, clean wheat. This diagram shows the endosperm portion from which we make the flour, which represents about 83% of the kernel, the bran, about 14.5% of the kernel, and the germ, which makes about 2.5% of the kernel. It is necessary to condition grain prior to milling by adding a small percentage of water to the grain and letting it rest for about 12 to 16 hours. This makes it possible to make a good, clean white flour free from bran and germ particles. Milling is done by grinding and taking the ground product and sifting it, making a separation. Each time the product is ground and sifted, we make flour. This is repeated many times. In a commercial mill, we use rolls and make the separations on nylon, silk, and wire on sieves. In milling, the products that we take off flour represents about 75%, about 24% bran and shorts, and about 1% germ. This movie shows many interesting shots inside the equipment in a flour mill. We hope after you have reviewed this movie that you will have a better understanding of the amazing art of flour milling. Let's look at the movie.
Before we can have these amber waves of grain, the wheat must be planted. Wheat is planted about an inch or so below the ground surface and may be planted in any position. However, the grain always grows from the germ end of the kernel and will always grow up regardless of the original position of the seed kernel. Germination time may be only 5 or 6 days for this much growth under ideal conditions. In 3 to 4 months' time, the wheat is ready to be cut and harvested when moisture and maturity are correct. In our present high production society, all wheat is harvested and threshed in one operation with combines. However, there is no more colorful event in our history than the threshing rigs of 50 or more years ago, and we bring you now an early threshing scene. The bundles of wheat were pitched by hand into the threshing machine. The threshing mechanism consists of a series of shaking screens and beaters to break the wheat kernels away from the stems and chaff. A blower provides the air to separate the straw and chaff from the wheat and blow it into the straw pile. Power was provided by this steam traction engine. Regardless of the type of threshing method used, the purpose is to remove the wheat from the stem and to remove the chaff as shown in this hand threshing operation. And here, one stalk of wheat can produce 35 to 40 kernels of wheat from one seed. The modern flour mill is the first completely mechanized and automatic manufacturing process known to man in which the wheat is converted into flour without the direct intervention of human hands. Modern transportation of domestic wheat is made with trucks and railroad cars. Here a truck is being unloaded. The truck ramp is tilted up to allow the wheat to flow out of the rear of the truck. Wheat storage to the mill by means of a screw conveyor. The processing flow diagram of even a small mill is complex and involved. Let us look at a simplified diagram so as to better understand the milling process. The two left-hand sections in this diagram show the flow-through machines in the wheat cleaning and preparation part of the mill. The actual flour milling operations take place in the machines shown in the next two sections of the flow sheet. The storage and load-out of the products are outlined in the final part of the flow sheet. The first machines are a magnet, milling separator, and stoner. Foreign iron pieces are removed from the grain by this magnet. The milling separator is a screening machine to remove particles both larger and smaller than the wheat. Here the operator is examining the oversized pieces of foreign material removed from the wheat. The screen provides this motion to make the separation. If you watch closely, you can see the wheat pass through the screen. The larger corn remains on top. The stoner removes the stones the same size as the wheat. Wheat and stones are separated by the action of this machine. Stones are made to travel uphill. Oats and weed seeds are removed on these machines. Wheat is removed from oats with revolving discs having pockets for selective separations. The wheat is picked up and the oats remain. In slow motion, we see the selective action of the separator with the oats being rejected. At the top of the disc, the wheat is discharged from the pockets. Rejected oats are discharged at the end of the separator. The seed separator is of similar construction, except the disc pockets are smaller. Seeds are picked up and the wheat is rejected. The seeds are discharged from the pockets at the top of the disc. Clean wheat is discharged at the end of the separator. Further cleaning is done on the entoliter and aspirator. Many milling products are conveyed by air, and this collector separates the air from the product. This entoliter machine destroys any possible infestation and scours the wheat. Air suction control is measured here. The wheat is being scoured in the entoliter cone. The cone is removed to show the revolving impeller. Under extreme slow motion, we see the action of the rotor as it throws the wheat out onto the impact ring. A view from below shows the impact of the wheat against the impact ring. A defective kernel of wheat is broken here. An aspirator is a machine to remove light chaff and hulls from the wheat by means of properly controlled air currents. Air is very important in the milling process, and many pounds of air are used to process each pound of flour. The grain cascades down through many air streams, and the light fractions are lifted out with the air. Wheat temper and final scourer. The correct amount of moisture is added for proper milling characteristics. Accurate water measurements must be maintained. Water is applied at the tempering conveyor and the wheat is thoroughly mixed. After tempering, the wheat is allowed to rest in bins for many hours. Just before milling, the wheat is given a final cleaning on a scourer. Inside the scourer, we see a slow motion study of the action of the beaters on the wheat. is conveyed in pneumatic systems much like a large vacuum cleaner. This is the pneumatic pickup unit. Wheat is separated from the air. An automatic scale is used to control the exact rate of flow of wheat to the milling system. Roller mills and sifters. The milling process starts at the first break rolls where the wheat kernel is first ground. Milling is a reduction system in which the product is ground, sifted, and purified many times before all of the flour is extracted. An extreme slow-motion study of the first break rolls shows how the layers of bran are peeled off and the white endosperm is ground up into flour. These conveyors pick up the products from the roller mills and carry it along to the next processing operation. After grinding, the products must be separated on a sifter. Many sifters are necessary for the various separations required in the system. Sifters are made with stacks of sieves for the particle size separations, and the gyrating action causes the stock to flow across the sieve. The stock comes in at the top and flows down over one sieve after the other, with the fine particles going through the sieve and the larger particles staying on top. The sieve mesh determines the particle size sifted out. The internal sifter flow is shown in this chart. Here we have break stock from the roller mill flowing across the sifter sieve. A slow motion close-up of the break stock being separated on the sieve. The fine particles pass through the sieve. Below the sieve, we see the fine stock coming through the sieve. The stalks flow out of the sifter into these spouts, and samples may be taken to check the quality of separation. This is the flour stock. And this is the coarse break stock for further processing. The next step in the flow is further classification of stocks on purifiers. The purifier actually makes 3 different types of separations: a size separation, an apparent density separation, and an air separation. The stock is introduced to the purifier on one end and distributed evenly across the inlet end of the deck. The purifier deck consists of a sieve assembly of various mesh sieves, with the fine sieves at the inlet end and the coarser mesh sieves at the discharge end. This provides a size separation. The action of the deck as well as an airflow through the sieve produces a density separation, and the airflow lifts up the very fine particles. Here we see the stock that passes through the sieves. This plexiglass purifier allows us to examine the action more closely. The stock is conveyed along by the action of the sieve, and the air suction through the sieve produces a stratification of the stock. The stock above the sieve is conveyed along, while the finer fraction passes through the sieve. Lightweight particles are lifted by the air suction and carried off with the air. The smooth rubber feeder rolls in place, we see an improved pattern with corn velocity approaching the speed of the rolls. Grinding of middling stock on smooth rolls provides another interesting study. In our first pictures, here we again use the camera mounted on the roll to observe the grinding action. The high-speed camera shows this grinding action very well. Smooth roll differential is 1.5 to 1. the smooth roll crushing action with 1-to-1 differential is revealed here. In all of these tests on middlings grinding, a vibrating feeder was used directly above the nip of the rolls. These pictures were interesting, but we wanted to further study the grinding action on a smooth roll by looking at the nip of the roll from inside the roll while it is grinding. Our first setup was to try to use a solid glass roll and photograph through the glass to observe grinding at the nip as indicated here. This was found to be unsatisfactory because of the optical problems involved. The successful method was to make up a plexiglass roll section mounted on a rotating heavy steel box structure as shown here. The surface of the plexiglass was accurately machined and highly polished to provide a smooth grinding surface. The camera eye can look through the steel box while it is rotating and get an undistorted view of the grinding surface in the same manner as we see these objects behind the rotating glass roll section. This glass roll assembly is installed in a small roll stand, and the high-speed camera is set up to view the nip of the roll through the hollow box structure while rotating. Electric timing circuits were arranged to start the camera and stock feeder at the same time. Here is the complete test setup in operation. And here is the smooth roll grinding action at the nip of the roll as seen by the camera. Note that the endosperm particles seem to explode upward as they are crushed. This is simply because the nip of the roll is below, and the only way the stock can go is up. This effect could be partly responsible for the boiling action of fine stocks above smooth rolls under heavy load conditions. The black spots that appear on some of the particles are caused by the presence of oil in some of the particles. This picture is the same as the previous one, except it is in color. The actual grinding time in these pictures was only about 1/4 of a second, and by means of the high-speed camera, we can watch the action for a full minute. Now watch the top center of the picture, and you will see a single yellow wheat germ being flaked. Here we have wheat germ on the right and fine middlings on the left. In this picture, the rolls are not close enough to do much grinding on the endosperm, but the germ is effectively flaked. This is the separated fractions as made by the sifter with the germ on the left. In this film, we have presented a few of the facts of roller mills in action, and we trust it will stimulate a desire to find out more, limited only by your imagination and desire to learn. A single cleaner in each section would be completely out of business if it were stuck. This next test covers the bolting action of turbo ground flour stock, where the coarse fraction has been dyed darker colored and then remixed before sifting on an 11 XX cloth. In these tests, screwballs were essential in keeping the cloth clean because the cotton cleaners would tend to paste over the openings due to their wiping action. When the sifter is shut off, the coarse, dark-colored fraction can easily be seen. The fine white fraction is bolted through the 11 XX cloth. Here we see flour slick samples of the separated fractions with a fine white fraction on the right, the coarse dark fraction in the center, and the original sample on the left. Leather pan cleaners are seen here with the top camera mounted on the sifter. The throw is 2.5 inches at 250 RPM without cloth or stock. Note that the pan cleaners appear to do little good as they always ride in about the same spot. Some flour stock was then introduced into the pan, but the action of the leather pan cleaners is about the same. It would appear that in most cases, pan cleaners are rather ineffective and could be left out entirely. The next tests cover the study and observations of stock on a special sieve from a Brabender experimental mill. The stationary camera shows the flow of purifier stock on a 48 GG cloth with a 1.5-inch circle at 234 RPM, which is the speed and throw the Brabender sifter is normally operated. Note the affected use of the flights or paddles to convey the stock over the sieve. Now our top camera on the sifter shows the action of the paddles. Sifter rotation must be clockwise with the arrangement of flights or paddles on this sieve. The previous test was repeated with just a handful of stock thrown on the sieve so we can better study the action. The stock pattern and flow are observed with our stationary camera. Remember, these tests have been made with a 1 1/2 inch circle at 234 RPM. These final scenes on the Brabender sieve were made with the throw increased to 2 1/2 inches at 234 RPM, which is more standard for our high-speed sifter operation. The effective action of the stock and flights at this throw indicate that a standard sieve with flights properly arranged might be helpful and increase capacity, particularly in the pan section of double discharge sieves or in other sieves where there might be a choke-up due to overloads. As our final scene of this film, we observe the Brabender sieve at the increased throw from our top camera position on the sifter. Here at the discharge end, the stock, lifted by the air suction, is clearly visible. Stock passing through the purifier sieve. The fine stock passes through the sieve near the inlet end. A coarser grade passes through here. A still coarser grade with more bran present. And the coarsest grade on the last section. The stock over the sieve contains mostly bran. The air liftings produce a flour dust product. The purifier stocks are shown here with a fine fraction on the right and coarse on the left. Note that the coarser fraction contains more of the bran, which will require further grinding, sifting, and purification to completely separate the flour from the bran. Stocks from some purifiers are high in wheat germ content. This stock is further purified on a gravity separator to separate wheat germ from bran. The wheat germ is on the right, the bran on the left. Pneumatic conveying equipment is an important part of the milling operation to transport stock throughout the mill. Here we see the collector units that separate the various stocks from the conveying air. The stock from these collectors go to a stream splitter that accurately divides the stream into a number of equal parts. The cyclone collector makes use of centrifugal force to throw the material entrained in the air to the outside, while the clean air is drawn toward the center and out the top. At the bottom of the collector cone, an airlock valve is provided to continuously discharge the product without discharging the air in the system, like a revolving door. Air from a number of collectors is drawn into large air trunks powered by large fan units. Large filter units make the final cleanup of the air before it is returned to the room. Further reductions are made on roller mills and sifters. This roller mill is grinding a middlings or sizing stock, which is really coarse chunks of flour. Fine flour is discharged below the rolls. Here in extreme slow motion we see the small chunks of middling stock being ground into flour. And here is a view from inside a glass roll to show how the small chunks are reduced to flour between the glass roll and the steel roll. The flour is sifted again to assure that all chunks are ground to the proper size. Any particles too large are reground on other roller mills. Bran is further processed on a duster, and the flour is treated in an agitator. A bran duster is a machine to dust off the last traces of flour from the bran. Beaters in this machine loosen the flour from the bran. The flour particles pass through the small openings of the screen, and the bran remains inside. An agitator is a device to treat the flour with a gas to improve its color and baking characteristics. Revolving paddles inside the agitator aerate the flour in the presence of the gas so that the gas can come in contact with each particle of flour. Enrichment feeders add important vitamins to the flour in accurate, specified proportions. In the complex milling system, there are many steps. Here are products from a first break sifter that go to second break roll. Sizings purifier, middlings purifier, redust sifter, and first break flour. Mill feed packing. The bran and shorts from the milling process are packed and sold for animal feed. Bran for animal feed. Shorts may include some germ and traces of flour. The bulk storage and load-out section. Before final storage and shipment, the flour from the mill is accurately weighed and recorded on this automatic scale. Flour production of the various grades are recorded on these instruments. From the mill, the flour is conveyed to the bulk storage building. This building contains many large bins to store the various grades and quantity of flour. On top of the building, many pipes direct the flour to the bins. A control panel controls the quantity and grade of flour to and from each bin. These pipes bring the flour from the mill. The various bin inlet pipes are shown here. To fill any given bin, a flexible pipe is simply connected from the proper mill outlet pipe to the bin inlet pipe. On the bottom of the bins, conveying equipment is provided to empty each bin. Flour is delivered from the mill in these large trucks. The flour is blown into the truck through this flexible hose. An opening is provided in the truck to let the air escape. The rapid flow of flour makes the hose surge. This load weighs 8,200 pounds. An important part of flour quality control is the physical dough testing laboratory, where flour quality is accurately established. This machine is a Brabender viscoameliograph. The farinograph determines the mixing characteristics of the dough. Dough strength is measured by the extensograph. The final supreme test of good flour is the baking of a good loaf of bread. Many ingredients go into a loaf of bread, and most important is good flour. dough is finally rolled out and placed in the pan for final rising. It is then put in the low temperature oven again for final rising. And in the oven for baking. And here is the final product, from wheat seed to a delicious loaf of bread. Please pass the bread. Let us remember that bread is truly the staff of life, and for over 5,000 years, civilization has followed the use of wheat for bread.